Hi everyone, thank you very much for being here. Very happy to see you. So tonight is the talk of Andrej, who came from Vienna, and as usually we have a warm-up talk from a student, and today is it's a warm-up talk from Aurélien. So thank you very much.
Thank you, Andrej, for the introduction. It's great to give a talk for the Quantum Club and a warm talk for Andrej. But let's get right into it. Okay, so I'll start with the fundamentals of wave function overlap and use this to talk about transfer integrals and how transfer integrals can actually quantify how electrons move from one atom to the other in a conductor, for example. Then we'll have a transition into the energy levels of solids and molecules and solids to talk about band structure theory and bandwidth. Bandwidth especially is going to be important in Andrej's talk because it's important for strongly correlated electrons in some materials. So to add on to this, we'll talk about bandwidth tuning methods, which are important to probe these to study these strongly correlated materials. Okay, so for wave function overlap, I put two free electrons separated from each other, really far away, and they're described by their wave functions. Basically, the wave functions here, they tell us where the electron is in space. Okay, but now what if we bring them together? When they're closer together, at some point we can see that the wave functions overlap and we have an overlap region. And this region where they overlap, the wave functions are actually in a superposition. So it's a place, a region in space where the electrons can coexist and they're actually in a superposition of states. So that's really basic, and what you need to retain is that they coexist in this overlap region. Okay, so for the transfer integral, lots of things on this slide, but I want you to look at the red curves first. I wanted to represent atoms, and they're really sharply peaked because compared to electrons, atoms will move like way less than electrons. And to these atoms, I have associated a wave function that describes the movement of the electron inside the potential of the atom. And actually, I've described them like this, but they actually look like this. But this is way simpler to represent. So I just decided to keep everything simple. One more point I want to make is that in atoms, we have the potential that gives us these orbitals. And to these orbitals, we have energy levels associated to them. They're discrete, and it's going to be important later when we see that in metals, in solids, they become actually a continuum. Okay, so we have two atoms and one electron here. There's still the potential that gives us this wave function, but let's say there's only one bound electron and it's here. Then, if we bring them closer together, we have, once again, an overlap region, but this time remember that we had one electron here, and it's moving around the atom, but at some point it's going to get here. And in this overlap region, it feels the potential of both atoms, and the wave functions are in a superposition. So if you ask the electron which atom are you bound to, it wouldn't really know the answer. So from there, it can actually move to the second atom. So in a way, this region is the place where it can transfer or hop to the next atom. So this is why we use the transfer integral T to describe, to quantify how electrons can hop from one atom to the other. Here you can, if you saw the equations earlier, you see that here there's an H present that wasn't there before. It's a Hamiltonian, and it's just because we need to take into account the potential of the atoms which make up the orbitals. Okay. Now we kind of understand better how electrons can move in solids. I've just represented a simple molecule here, but how they move in solids. And So we know that since T represents how they move, it represents in some way the kinetic energy of the electrons. But let's talk more about energy and energy levels of a molecule, for example. I mean, to start. First, you have to know that molecular orbitals are not the same as atomic orbitals because they're a superposition of atomic orbitals. And I have two simple diagrams here. The first one is for an anti-bonding a bonding orbital and for an anti-bonding orbital. And they actually have different energy levels. And you can understand that by saying that, okay, this is the electron density around the atoms. And this density is centered around the middle of the molecule, so between the atoms. So you can imagine the electron kind of pulling the atoms together. And so it has a lower energy, and because it's a more stable configuration. And then quickly you realize that this is not the case here, and they're more on the edge. I mean, the electrons will be centered on the edges of the molecule and will kind of pull the molecule apart, and it will be a higher energy state because it's less stable. Okay, so I talked about those two energy levels that are separate, and so we actually have one low energy level and one high energy level. One thing that's also important is that this energy difference here will get larger if you push the atoms closer together. But for now, let's talk about what happens in a solid when you have Na numbers of atoms and Ne electrons in total. Because of Pauli's exclusion principle, we know that Ne electrons means Ne states. But since in every energy level, you can have a spin up and a spin down electron, you'll have Ne energy levels. But still, that means that if you have a finite energy difference and you're trying to put Ne over two states, when you have a solid where you have Avogadro numbers, many times Avogadro's number of electrons or of atoms, you'll have so many states in a finite energy difference. So you'll have something that looks like a continuum. And we get into the idea of a band, a continuous band, and so band structures like you may have heard about. To finish this slide, I want to talk about this energy difference, which we call the bandwidth, now that we have a band. And this bandwidth is proportional to the transfer integral T. And you may already have guessed it. It's because I mentioned that when you bring the atoms closer together, the bandwidth gets larger. And that's because you bring them together, there's more overlap, and the transfer integral gets larger. And since they're proportional, you have that the bandwidth also represents the kinetic energy. Okay, that's too bad. Okay, so now let's actually get into electronic band structures really quickly. Here I plotted, here there's a plot of a random material. It doesn't really matter for our purposes. We just have continuous bands and bandwidths. We have energy on the y-axis, and we actually plot these band structures in momentum space with specific high symmetry points. So just if you've never heard about it, this is what they look like. And this is where we see the bandwidth. And band theory is really useful to describe materials, metals, semi-metals, insulators, semiconductors. But they all assume that electrons don't see each other, that their interactions can be neglected. But that's not always the case. What happens in a strongly correlated material is that band theory fails, and we actually see phases of matter that we didn't expect to see there. So, for example, the Mott insulator is supposed to be a metal, according to band theory, but since it has strongly correlated electrons, you actually see an insulator. Here I put a phase diagram from one of Andrej's articles, and yes, everything got messed up, but here you have temperature and electronic correlations, and I need to introduce them. Is to talk about strong interactions, we need to add an interaction potentials to our model. So you may have heard of the Hubbard model, and So you may have strong interactions, but whether the electrons are correlated or not is going to matter but on the ratio of U, the interaction potential, and W, the bandwidth, so the interaction and the kinetic energy. And those are called electronic correlations. And as you see that you get into a more correlated material, you get a more Mott insulator, and then you make the bandwidth larger, and this gets lower, and you get back into a conduction regime. And so it's really interesting to look at the phase transition between the two to really learn more about the properties of the material. And yeah, this plot is a great way to go on to my next slide, because here you see you have pressure to describe. You have pressure that gets larger, and as the pressure gets larger, the correlations get smaller. So let's talk about that. Okay. Here I've put two methods of tuning this parameter U over W. Here I want you to look at the two gray atoms, and we're going to look at how they overlap. And we have a green spacing atom in the middle. So when we push with pressure, we push the material together, the atoms get closer together and they overlap more. So the bandwidth is going to be larger. So we see that the electron correlations decrease, U over W decreases, and maybe we'll see a phase transition when we apply this pressure on the material. And another way of doing the same thing actually is taking the gray atoms and putting no pressure, but instead we put small spacing atoms. And what happens is that there's more space for between the two gray electrons. Between the two gray atoms, there's more space to actually get closer because the spacing atom is smaller. And same result, the overlap gets larger. Okay, so that's two ways of probing it. And if I go back here, if you apply pressure like Andrej did, you actually see that you have a smaller correlation because it's the overlap, and therefore the kinetic energy gets larger. Okay, so to quickly summarize, we looked at overlap integrals, overlap of the wave functions for transfer integrals to understand how electrons move a bit better, and this also helps us understand what band structure is. And really, I introduced, I think, just enough band structure to understand where it fails. And where it fails is where it becomes more interesting to talk about correlated material electrons. And since we don't have band theory to talk about it anymore, we look at these phase diagrams and we tweak these electronic correlations to actually explore these phases of matter. So that's all for me. Thank you for your attention, and now I want to give the floor to Andrej.
Good. Thank you very much. It was a great introduction, and I'm happy I don't have to say the stuff again. Some of it naturally will be repeated a little bit, just to keep it flowing. So, welcome everybody. I'm happy to be here again. I see one of my former students from Vienna here, Annie Chen. So, and thanks to Anna for inviting me to this nice event. And today I want to give you an overview of organic quantum materials, which typically look like this here. So these are materials which are built of organic molecules. Wait, let me take my time so that I know how long I can say. They can be layered, they can be stacked in one dimension, they can be even three-dimensional. And eventually they can build correlated phases like a Mott insulator, and which one can tune towards a metallic state. Let me quickly introduce myself also to the people who don't know me yet. So I'm from Germany, from Berlin, but I grew up in Vienna. But for the studies, I did not study in Vienna. I went to Munich, did my bachelor there. Then I was in Switzerland during my master at ETH Zurich. I did my PhD in Stuttgart, in Germany, and then I went further to the west, to Los Angeles, to do postdoc for almost 3 years. And then I was happy to get a position in Vienna, so back home, where I am currently working and doing my research. So it's a very nice place to live and also to work. So there's the city center of Vienna. So here you see the Wiener Musikverein, where you have the New Year's concert every year. And from my office, I can see it right there. So it's, of course, I cannot hear it because it's closed. Yes, and there I'm doing research on correlated electron systems. Here we have a picture of some group members working on organics. So as I mentioned, Annie-Chen managed to get here from Lausanne. And I have collaborations with people in Japan who provide me these organic samples. Also with my former PhD advisor, Martin Dressel in Stuttgart. Also with the group in Los Angeles with Stuart Brown, some other Japanese collaborator, and of course, people in Vienna. I'm doing also other type of research on, let's say, thermoelectric materials, on inorganic materials, but today this is only the organic part that I'm looking at. So I'm studying these materials with different spectroscopic techniques, which cover the entire electromagnetic spectrum. So at low frequencies, well, apart from transport, which everybody is doing, I'm doing dielectric spectroscopy, where we can look at dipole reorientations on bigger scales. Then in the radio frequency range, I'm doing nuclear magnetic resonance, where we can excite the nuclear spins and learn how the electrons around these nuclei behave. Higher frequencies, I contributed to some electron spin resonance work, where one can excite directly the electrons. And then we go to the optical range, and terahertz frequencies, infrared frequencies, and up to the visible range. So in infrared, we typically can look at phonons and also at the electronic excitations. And then the higher we go, the more, the larger energy gaps we can cross. So in Vienna, we have also very large experimental equipment. So if anybody of you is interested in some of this, just approach me. And it's a very nice place to do solid state experiments. And my focus, as I mentioned, are the spectroscopies. This is the energy and so the frequency and temperature range, which I am typically studying. So at low frequencies, we have transport, then at radio frequencies, nuclear magnetic resonance. Radio frequencies really means the frequencies that you measure, that you get in the radio. So sometimes in an experiment, you have to shield out these 100 megahertz frequencies because they are just noise for our experiment. And then at higher frequencies, optical spectroscopy. And we can go down to liquid helium temperatures with all of them. And of course, with transport and NMR also to millikelvin temperatures. So, and now let me quickly walk you through what is interested in electrons in solids. Then I will show typical phase diagrams of correlated electron systems. And then the main part is why organic quantum materials are so nice that we can study all these physics altogether. And so we will see how nicely tunable they are. One can chemically tune them, physically tune them, apply doping, which is not that big in these materials, but still possible nowadays. And then show some examples of correlated electron phenomena, which are nicely studied with the organics. So just since we are in Geneva, I wanted, and CERN is not far away, I just wanted to review a little bit with what we are working in physics. So we know these elementary particles, and in principle you could say, well, if we know all these properties, we could predict how any big amount of these elementary particles behaves together. However, and the nice thing is, if you put a lot of them together, they do not behave as individual particles, but they form some collective phases. So they become a metal where particles can move around. They can form some insulating phases. They can form unconventional superconductivity, also conventional superconductivity, magnetic orders, charge orders, etc. So we have these emergent phenomena because of the interactions of these particles. And just as examples, in a common solid where we have a band structure, which was nicely explained before, depending on the details of the band structure, we have, for instance, the curvature of the band, which is the inverse of the mass of the band. And therefore, we can describe electrons in solids by quasi-particles with spin 1/2 and charge E, but the mass is a little bit different than the free electron mass that we have here. Then we also have an analog in solids of a Higgs boson, so a superconductor. Actually, in superconductors, this Higgs mechanism was discovered before it was applied to the elementary particles. And the essence is that if a photon enters a superconductor, it acquires a mass. It is not massless anymore. Vice versa, if we build a material with linear dispersion, the electrons in this material, in so-called Dirac materials, they behave like photons in vacuum. So essentially, they move very quickly and as if they would have no mass. So we can do vice versa, these tricks. And there are also even more exotic things like Majorana fermions, which are possible candidates that would describe the neutrinos. So particles being their own antiparticle. And there are even some materials, like honeycomb materials, where it was suggested that the elementary excitations in solids are Majorana fermions. So when we now have one particle and we put it in vacuum, like a free electron, then we know exactly its properties. It has a well-defined mass, and we can define its energy by just the velocity, so this momentum. If we now have electrons in a common metal, like silver, gold, etc., then we can describe it according to the band structure, as I have shown. Just we have a mass which is slightly different than the effective mass, but it's very close. So you can consider it like humans, which are not very densely walking around. They see each other, but they do not very strongly affect each other. If we have a lot of them, then the motion of one particle is affected strongly by all the other particles, and this can be described by an effective mass much bigger than the free electron mass. And in heavy fermion systems, this can be even 1,000 times bigger than the free electron. And yeah, the question is, how often do they scatter? Here they never scatter, here they rarely scatter with each other, and here they almost at every lattice site they scatter with each other. So this is a very dominant interaction. So just as an illustration, here you have a quasi-particle which is light, and here it is heavy because it is not moving alone, but it is kind of pulling behind all the other electrons it is interacting with. Then, if we have strong correlations, we can have many interesting phenomena. And of course, the idea is that we would like to tune these interesting phenomena and apply them in some way in reality to some quantum computers and etc. So, and the idea is now, how can we tune them? And I will focus on this concept of bandwidth tuning, which is primarily dependent on the distance between atomic sites. So as we just heard, the overlap of the wave functions determines how delocalized they are, how the probability is that they are simultaneously on site 1 and 2. And if we put them closer to each other, this overlap just grows. And in the end, this is the typical phase diagram that we conventionally see, or unconventionally, in correlated electron systems. So when we have strong correlations, so correlation increases to the left, then we have typically some types of ordering. So magnetic, charge, etc. So many possible degrees of freedom. And as we suppress this order, as the correlations get smaller, then we turn metallic, and almost in all cases, we see superconductivity of unconventional type. And this is why we are interested in these materials, because we want to understand how all this works. And we do this typically by synthesizing materials in different parts of the phase diagram. We can synthesize one material here, one here, one here. So this I will call chemical tuning. And the common way to do this is, for instance, bandwidth tuning. We substitute particular atoms by bigger or smaller ones, and therefore we tune the distance. Another way to tune them is by doping, by having atoms with more or less charge carriers than the one that we are substituting. And as a result, we can study this phase diagram by different materials. So, for instance, the compound in black, I will not pronounce it, but it's one of these organic compounds. At zero pressure, it's here. When you apply pressure, you can tune it all the way up to here. And so you cover this part of the phase diagram. Then the compound in red, it starts here, you apply pressure, and then it covers this range. And the compound in blue, it starts here, and then you cover this range, and you can even go further on this metallic side. And the nice thing is, we understand by now this physics. So this is not just like a number that we measure in the experiment, what we read from the screen, but this is really the units that we use in theory. So the Coulomb repulsion divided by the electronic bandwidth, and the numbers here are determined from experiment. This is the important thing. Also here, temperature divided by bandwidth. So we can study these organic materials up to temperatures where we have 20% of their electronic bandwidth. So in oxides, this, as we will later see, this is not possible. Then, in order to study, I showed you this phase diagram with pressure. So we can take this material, apply pressure, and we will go to the right. Then we study this transition line that we have here, for instance. I focus here, I point out hydrostatic pressure. So we have it in a liquid or in a gas, and the pressure is homogeneous. So it's, we assume primarily that the anisotropy of the material does not change. Yeah, the main thing is you can increase the pressure only from left to right. You cannot apply negative pressure, as you understand. Sorry, other way. And then there's another tuning technique, which is uniaxial strain tuning. If you glue a sample on the right and on the left side, and then either you push it or you pull on it, therefore you can anisotropically extend or compress the atomic positions, and this way you can go both to the right and to the left in the phase diagram. And this technique, this can be done by piezoelectric strain cells, which we can operate nowadays down to millikelvin temperatures. So we can really tune a material which sits here to the left and to the right, going through the superconducting dome, and do this from millikelvins up to 100 Kelvin. So these are the capabilities of the, let's say, 21st century that we are exploiting. And as a result of research over the last, let's say, 50 years, there are many different correlated electron materials. So like heavy fermions, where you can tune magnetic field and get quantum critical points. There are iron-based superconductors, where you have some magnetic order, and then you have some superconducting dome, so, changed by chemical substitution here. In the cuprates, we change the doping and have high temperature superconductivity, and the organic conductors, where we can use pressure or any of the other tuning techniques, as I mentioned before. So, and as we see from all these examples, these phase diagrams look more or less the same. So in all cases, we have this ordered phase, which in all cases here is magnetic order. Also this part is a magnetic order. Then we have superconductivity and we have a metal. So it seems the physics in all of them is more or less the same. But of course, we try to study it circumstantially, and so we need very tunable materials. Today I will focus on these phenomena, so the superconductivity, metal-insulator transition, then magnetic order, and also how we can frustrate it and break this magnetic order. So the ordered phase, as I mentioned, it can be magnetic order, or it can also be charge order with more positive charge on one side and more negative charge on another side. So it can be just a Mott insulator where you have a gap between. So you, as I will later show a slide on this, you can prevent two electrons sitting on the same side, but this does not involve changing the charge or the magnetism on each side. And all these phases can be suppressed when going from here to here, and then we get a metal. And the metal, the only, but also the, in most cases, proper theory is Fermi-liquid theory. This is what we understand, and often we are interested in the deviations from Fermi-liquid theory, which occurs typically in the range right above the superconductivity. Yes, so the main point is that we can look at the electrons, say they have a different mass. The mass increases as we go towards the phase transition, and then at some point it's not a metal anymore. Yeah, and in between we have the superconductor, and the interesting thing is that the superconductor, I mean, it has zero resistance at zero frequency, it has an energy gap, and electrons are paired in bosons and Cooper pairs. So they have spin equals 0. And the superconductor is kind of a chimera between a metal, where we have mobile electrons, but it still has a gap, like an insulator. So, and this way it can behave differently, that it does not scatter with the lattice eventually. And yeah, so it seems to require both this ordered phase and also the metal to pair up. So the superconductivity was observed already, discovered more than 100 years ago by Kamerlingh Onnes, first on mercury, because mercury was a very clean material and he was the first who could cool it down to these low temperatures. But nowadays we know that almost every element is superconducting, so this is something pretty common. But usually these temperatures are not very high, so 5 Kelvin, then we have somewhere close to 10 Kelvin. And yeah, so these are not very high temperatures. But we know nowadays from BCS theory that these, the superconductivity in these, the conventional superconductivity is driven by electron-phonon coupling, and it depends on the mass of the atoms involved. So if we go from heavy atoms to light atoms like boron or magnesium, which are very high, then you can get pretty high transition temperature. It was even predicted that hydrogen could go to room temperature, and there have been in the last years also some suggestions that this can be true. But there have been also a lot of results which were afterwards withdrawn, or I mean, not confirmed. So yeah, and where does it come from? So these two electrons interact via the lattice distortion, via the phonon. So one electron, let's say it starts here, then it attracts these positive ions. These ions move there, but the ions are much slower than the electron. Then the electron goes away, but the positive polarization in the lattice remains, and it attracts another electron, this one. And in the end, this phonon is reabsorbed by the second electron, so there is no net energy loss to the lattice, and this way it's superconducting. And the phonon itself shows up in this energy scale here, the Debye energy. So if we take lighter atoms in the same element, so a different isotope, then we see a change of Tc, which increases. Simply due to this relationship that the vibration frequency is proportional to 1 over square root of the mass. And this brings us to the organic materials, now after a little bit more than 15 minutes. So it was predicted in the 1960s that organic materials, because they contain light elements like hydrogen and carbon, could be superconductors. And therefore, people tried to build materials which are on the one hand metallic, but consist out of organic molecules. And with the expectation and hope that we could build high Tc from that. Here we see in general how the materials of superconductivity evolved over the years. Here we see a few organic materials like these fullerenes, fullerides. And if we focus in more detail on the organic materials, from the 1980s on, there have been a lot of these organic systems discovered. And yeah, the highest Tc was from these C60s. I think this data point is due to the Jan-Hendrik Schön collusion, so this is not correct. Yeah, these data points here are correct. So and we will focus on these materials here, which have transition temperatures up to, let's say, 10, 15 Kelvin. And yeah, in the very first organic superconductor which was discovered was this quasi one-dimensional material, TMTSF2PF6, which showed under pressure a TC of 1.2 Kelvin. So Bechgard and Jerome were the people who discovered it. And since then, many materials which are rather similar to them have been discovered. Here's this first measurement. So you see under pressure that superconductivity occurs below. And the nice thing about the organics is that we can tune them. So not all of them are superconducting, but these organic systems, they exhibit all type of phases, and we have tools to tune the material to the right slot in the phase diagram. So how do they look like? So in the case of these one-dimensional TMTSF materials, you have an organic molecule facing another organic molecule, and they are face to face, and in between we have some anions. So the organic molecule itself, it has some pi orbitals which are perpendicular to the molecular plane. So, and if you now put two of these molecules together, then these orbitals overlap and hybridize, and then you can actually make the electrons move from here to here. And if you have, in the case like here, a chain, then you can have a quasi one-dimensional electron system. The point is that the molecule is in this phase, it has only the right orbitals and band filling if we take away a little bit of charge, half a charge per organic molecule. And this charge is compensated by the anions that we have here. So we have always salts. I mean, the cuprates, they are also ionic, so you have oxygen 2 minus and copper 2 plus. But here you have these organic molecules are positive and the anions are negative. And there are different types of these molecules. So it started with these smaller molecules, TCNQ or TTF. And then people started building something on the ends of the TTF, like some additional methylene groups on all 4 points. And then they later built another ring on outside, which is then this so-called BDT TTF molecule. And from this one had a very big variety of physical systems. If we look on these orbitals, so most of the molecular charge is centered around these carbon-carbon double bonds in all of these molecules. So this will be important for the later points. Good. So here we have some more organic molecules. So they can become quite long and complex. And they can even look like a football, C60 molecules. And of course, depending on the size and the particular elements, whether you have sulfur or selenium, for instance, they have slightly different properties. And this can be used, if you understand what you're doing, to tune through the phase diagrams. So these small molecules typically lead to one-dimensional chains, quasi one-dimensional electron systems, so the TMTTF or the TMTSF molecules. Then if we have these BDT-TTF, or let's call this DMIT, they form layers, quasi two-dimensional, separated by anion layers. So they are very similar to the cuprates in this regard, so they are also quasi two-dimensional layers. And then these C60 molecules, you have 3 like potassium or sodium or other alkali atoms. And then you have 1 buckyball, and these form 3-dimensional cubic arrangements. The problem about the fullerenes is only that they do not form single crystals. Yeah?
Simple question. When you say quasi one-dimensional, quasi two-dimensional, what do you mean exactly?
So the electrons in this system, they move only along this direction. They do not move in this or in this direction.
And they are quasi just because they eventually form three-dimensional?
They form a real millimeter-sized single crystal, and so the single crystal is of course three-dimensional. The thinnest side, so typically for the quasi 2D ones, they look plate-like. But of course it's a 3D crystal, and there is some finite probability of an electron hopping also in this direction.
Is it important, this finite probability?
It's so the resistance going from here, so in this direction, is factor 1000 higher than the resistance in this direction. So they are very anisotropic, and that you can one sees that most of the relevant physics is for electrons which can move in the parallel to the layers. And here, in these quasi 1D systems, you see you can even validate all these Luttinger liquid physics, which has been done in the late 90s, I guess. So they really behave like electrons along 1 or 2 dimensions in this case.
Why is it interesting to have a look at 2D and 3D materials when you're only focusing on this one direction?
On the one hand, if you have low dimensions, you naturally have large correlations. That is one thing. So the bandwidth is proportional to the dimensionality times the number of so essentially the number of nearest neighbors. If you have 2 nearest neighbors from this side, you will have so dimensionality times t, and the dimensionality determines how many nearest neighbors you have. Because if you can only go up and down, you have 2 nearest neighbors. If you can go left, right, and front, back, you can have 4 nearest neighbors. And if you have 3-dimensional systems, in a cubic case, you have 6 nearest neighbors. So naturally, the bandwidth is larger if you are higher dimension, and then you just have a common metal. But the correlations are typically only there if you have a small bandwidth, and this we want to achieve to realize this physics. Was there a second question? No. No. Okay. Or did I answer everything?
Yes.
Yeah. Okay. Yes. Then, as I mentioned, they form these. In the case of BDT-TTF, they form these layers. And for the anions, we take something which has a charge -1, like I3 minus or copper NCS2 minus, and these can then even form some polymeric networks. But in general, if we look at the 2-dimensional quasi-2D systems, within these conducting layers of organic molecules, electrons can move. The anion layers have a completely filled shell. The electrons cannot move here. There are no states for them. And yeah, so you can consider it just like a conductive layer. So how can we study different physics? So the simple thing is, you can synthesize materials with different anions, and these anions can have different size. So for instance, copper NCN2Cl, and then you have here instead of Cl bromine. So this means that bromine has a different size than chlorine, and therefore you change the position. Yeah, and they have a different size to iodine 3. And in the end, it's only relevant how the change in the anion layer changes the distances between these organic molecules. And in the end, it was seen that one can study these phase diagrams, and these materials are just at different positions. But they, in principle, or no, in reality, they exhibit the same physics. Here for essentially half-filled electronic systems, and here for quarter-filled systems. So in quarter-filled systems, instead of the insulating phase is a charge-ordered phase, it can also turn metallic. It also has superconductivity. And here you also have just slight changes of these molecules, and you can study the entire phase diagram. Then one can, I mean, what I mentioned here is that all of the X are substituted, but you can take only some part of it. You can make some part of the anions with bromine and with chlorine, and this way you can continuously go through this phase diagram. This bromine compound is on the metallic side, the chlorine compound is on the insulating side, and when you make a mixture of bromine and chlorine, then you get right at these intermediate positions. And this has been studied in great detail, and the physics is really the same. Of course, it also provides a measure to study disorder effects, because these bromine and chlorine, they are randomly inside. And if you have the possibility to compress a material, go to a different place in the phase diagram, but also to, without compression, just drawing a different material, then you have different ways of studying disorder and correlations independently. Here's a different type of substitution. This ET is the same as BDT-TTF. Then you have silver 2CN3 or copper 2CN3, and these two mixed. And the copper version under pressure becomes metallic and superconducting under half a GPa. The silver version under more than 1 GPa, and the mixture of them becomes superconducting even before. And interestingly, it shows an increase of the superconductivity. So such an increasing tendency with pressure is a sign in these materials that this order is relevant. And yeah, if you have 50-50 atomic substitution, then it looks quite disordered. Yeah, and just for these two cases which I have shown, in the general phase diagram, this chlorine-bromine substitution covers this range in the phase diagram. The silver-copper covers this range in the phase diagram. So depending on which are the two end members, you can study a different range. Then for the quasi-one-dimensional systems, this is the very rich phase diagrams. So on the left side, you have TM-TTF, the Fabry salts. And then here you have the TM-TSF, the Bechgard salts. So the Bechgard salts are the ones which become superconducting, but you can reach there in principle also by pressurizing these Fabry salts. But you really need quite some pressure. So this is 5 kilobar, half a GPa. So you need several GPa to go from here to here. And they have correlated phases which go from charge ordering, localization, which means Mott transition, spin piles, so a kind of valence bond ordering, antiferromagnetism, spin density wave. So, and they even change their dimensionality. When you press them, they are first one-dimensional. At higher pressure, they become two-dimensional, and afterwards, they really behave like a three-dimensional solid. So, meaning that the conductivity along all directions is more or less the same, the electrical conductivity. Yeah, and these different ions that we have here, PF6, ASF6, SPF6, tantalum F6, well, they just go vertically down. So phosphorus is smaller than arsenic, arsenic smaller than antimony, and smaller than tantalum. So the biggest anions are on the left, and this means that they make the largest separation between organic molecules. So we have the smallest bandwidth. And when we apply pressure, we can go back from this position to the right. What is neglected in this phase diagram is that the anions themselves, they can also lead to structural phase transitions. So if the anion, for instance, is non-centrosymmetric, like a tetrahedral, like here, it can, one of them can point to the left, one to the right, one to the left, and this can give an additional phase, which is not indicated here. But this is a structural phase, and the phases that we have here, they are really driven by electron-electron interactions. So, and this is what we are mostly interested in. Good. Then also with these systems, we can do partial anion substitution. So between this antimony and the arsenic, we can just randomly mix the two. So make a mixture of arsenic and antimony containing anions. And these we really end up in the middle between the two. So by just randomly putting it here like I showed here. The nice thing is we can, if we have such a sample, we can just look at the vibrations, which includes the antimony or the arsenic. So if we have the clean arsenic system, we have only a vibration mode and at high frequencies. The wave number is inverse wavelength. Then if we have the antimony containing anion, we are only at low frequencies. And the sample that we synthesized contains both low frequency and high frequency phonons. So we directly know that we have all of them there. And from this, from the height of these peaks, we can even quantify how many. In this case, it was about 30%, 30 to 40%. So it's closer to this one. And if we look at this transition temperature, so the transition temperature from the metallic to the charge-ordered phase, the transition temperature here is 160 Kelvin. For the red one, it is 100 Kelvin, and for the compound in between, it is somewhere around 120 Kelvin. So the physics is indeed nicely realized this way. Interestingly, the value of how much charge is disproportionate between one molecule and the other ends up like in the red molecule, in the red version, so in the arsenic compound. But these are details. Then, so here we were looking at the anions, the spacers. We can also tune this material by varying these organic molecules. So this is the common one, but we can, instead of sulfur, put selenium. And we can put selenium symmetrically or only on one side, or we can put the selenium not on the inner part, but on the outer part. And this will give different physics. Because the selenium has bigger orbitals than sulfur, and therefore it enhances the bandwidth. So if we have here a material which has a charge order transition, this alpha triiodine sample, the common sample is at 136. Then if we put this, this one with only 2 seleniums, it is around 100 Kelvin, and if we make 4 seleniums, then it is suppressed to 70 Kelvin. So it is efficiently working as an increase of the electronic bandwidth, so the correlations are reduced and transition temperatures go down. So here you can see the different transition temperatures, and these molecules, so with 4 seleniums, we have very big orbitals. Without seleniums, we have small orbitals, and with 2 seleniums, something in between. And of course, I mean, we can change the seleniums in the middle, we can change the seleniums on the outside, we can also change the hydrogens to deuteriums. This is also something we can do. If we use deuterated molecules, use another example for this bromine-containing sample, hydrogen is more on the metallic side, deuterium is more on the insulating side. So by just using the same molecules with deuterium instead of hydrogen, we turn it from a metal into a Mott insulator. A very small change, but it slightly changes the lattice constant, and here we are actually very close to the transition. This is why it works. And if we put the selenium on the outer positions, it interestingly goes to the left side. So it goes to lower bandwidth. And the reason is that most of the charge is on this double bond in the middle. And if the overlap of the molecule is on the outside, the distance between these inner parts of the molecule is increasing. So eventually the overlap is getting smaller. There are a lot of possibilities to play around, and the last years have really given success to go to selectively study the phase diagram by doing these chemical substitutions. So yeah, here's one example for this substitution, outer seleniums. So we start in the metal and superconductor, and by putting more of the molecules, it becomes a Mott insulator eventually, and superconductivity goes away. So we really go to the left side. But when we use these STF molecules, these ones, then we start from here and go to the metallic side. So this is, superconductivity is also suppressed, but the sample remains metallic in the end. So these are very nice studies. Another example where this was done is we started in a Mott insulator and then substituted in a triangular lattice compound, and we ended up very far on the metallic side, which allowed us to study this so-called bad metal regime in great detail. And yeah. So you can see if you have small contents of these molecules, it is an insulator, but if you increase the content, then at some point you have metallic resistivity. So it drops with low temperature, and then it stays metallic all the way. And it even shows this quadratic temperature dependence associated with Fermi-liquid transport. So physical pressure. as I mentioned before, we can go from left to right from one sample. I mean, we can also start with this sample and go from left to right. This way, interestingly, one can also stay at a constant temperature and change the pressure, therefore looking how the resistance changes. And then by taking the steepest slope, you can define, this is the transition from a Mott insulator to a metal. And you do this at the different temperatures, and this way you map the entire phase diagram. At low temperatures, by the way, the Mott transition has a first order transition. And above the critical endpoint, it is a continuous transition. And when we look at this, we can do continuous pressure sweeps by using helium gas. So these are really low pressures. I mean, of course, it's still several hundred bars, but for solids, these are very low pressure scales. A little bit higher pressure can be used, can be applied by oil pressure cells. But the oil has the problem that when you cool it down, the oil freezes, and then you cannot change it at low temperature anymore, as we can see here. Helium gas, you can increase and reduce pressure as you want, until at low temperatures the helium also freezes. But yeah, below 10 Kelvin or something. But it is strongly pressure dependent. But if you have a sample at a different part in the phase diagram, this dashed line, this would be this part. And if you apply in an oil pressure cell, you start at high pressure, then you cool it down, the pressure drops a little bit, and then you end up at the same place. But the problem is you can change the pressure only at room temperature. So at low temperature, you cannot go left, right. And therefore, another powerful tool is to apply uniaxial strain, as I mentioned before, because then you can go from left to right without warming up. Good. On the organics, uniaxial strain was applied as well. So in this case, we put one very thin sample on a plastic substrate. Then we bend the plastic substrate at low temperature. And by bending it, the outer surface, the outer length becomes larger. So the sample is stretched essentially. And by this stretching, we can study this phase space in blue here, right around the Mott transition in great detail. So in this small range, we had like more than 10 data points, which are plotted on the left side. So these are, this is a really precise technique to study small changes in the phase diagram. Then we also succeeded recently to glue an organic sample, which is in this range. I mean, it's based on carbon, so it looks like a piece of coal. I mean, this black stuff on the right side is the glue, which we need to fix it to the strain cell, and then we push it this way, and the inner part here is compressed. And we get the phase diagram that we would also get from the, so we have a Mott insulator, we have here the metal, and here this phase boundary, and we reproduce the same phase boundary, and we suppress the magnetism as in the pressure measurement. So this was done on a big sample, which is freestanding, whereas the previous measurement was done on a very thin sample on a substrate. Of course, on a substrate, you have other problems. But this is like a technique which is very flexible, and here we showed that it works. Good. We can, in general, to summarize, these organic conductors are very tunable, so you can apply pretty low pressures, less than a GPa, and you study all the superconductivity and suppress it. You can apply pretty small magnetic fields up to a few Tesla, and you suppress the superconductivity. And in the phase diagram, you can study a pretty large range, because 300 Kelvin of temperature can be comparable to the bandwidth already. So 30–40%. This means that in the phase diagram, you cover a much higher temperature range than for the inorganic systems. Vanadium oxide, a well-known Mott insulator, studied here from 200 to 500 Kelvin. So the critical endpoint is around 400 something Kelvin. Is just in this very small part of the phase diagram. Because the oxides, the inorganic materials, have a very big electronic bandwidth. And since we divide by bandwidth, if W is big, then you have just a small range that you can study. And the organics can study a range which is factor 10 higher, which makes them very useful. In the oxides, factor 10 higher temperature, 5,000 Kelvin, the material would be melted for a long time already. Okay, doping. In correlated systems, like in the cuprates, doping is used to study the superconducting dome, or to make it superconducting at all. The organics are mostly studied by bandwidth control, so by applying pressure. And this way one can go from the Mott insulator, you can go either to the Mott insulator by changing the bandwidth vertically, or you can go in or out by changing the doping. But the problem is cuprates cannot be pressurized to become metallic, and vice versa, organics can usually not that well be doped. So they have exclusively different parts of this phase diagram which they study. Even though the physics is pretty similar, so they have deviations from the Fermi-liquid regime at high temperatures in both cases, bad and strange metal, and at low temperatures they also show the Fermi-liquid and they show the superconductivity in both cases. And but it would be more interesting if we could have a material where we can change the doping and the correlation strength and possibly even the frustration. I will come to this in a bit. Let me just mention that the organics can by now also be doped, and it was shown that they show electron-doped superconductivity and hole-doped superconductivity, and you have electron-hole asymmetry like you have it in the cuprates as well. And also binary graphene. So the organics can by now be also doped, but these experiments are more difficult. And another thing is the organics can be, there are many materials which are close to a triangular lattice, so you can really study frustration effects in the organics, which in cuprates on the other hand is not possible. And yeah, here we recently doped the frustrated Mott insulator together with Kawasugi-san. And so this is a triangular lattice material, this is a square lattice material under doping. Good, and then let me quickly go through these few examples. There are a lot of organic superconductors. So this paper lists up 120, which have TCs of 2 Kelvin up to 14 Kelvin. So this list here in the paper is 4 pages long. This, I will not go into details here, but the superconductivity is similar to the cuprates. It's D-wave superconductivity with a nodal superconducting gap, and which is evidenced here by nuclear magnetic resonance. And it looks very similar also to these Fullerites, even though they are three-dimensional. So the phase diagram that was plotted here was showing volume, which increases from left to right, but if we apply pressure, we reduce volume, so we have to flip it. Then we have here on the big volume the Mott insulator. When we apply pressure, we turn it metallic, and the superconductivity in between. So this looks essentially the same as in the organics, as in these two-dimensional organics. Interestingly, we can have this phase diagram either with magnetism or without magnetism. So it looks like that the superconductivity comes from the metal-insulator transition and not necessarily from the antiferromagnetism. Then we can have quarter-filled systems, which is quite interesting. So from the chemistry point of view, the anion has one negative charge. So the BDT-TTF molecules must have in total also one positive charge. This way one can realize charge ordering and superconductivity in between, which we will see in a second. But first we go to the Mott transition. I think this we can skip because we are far in time. So yeah, the Mott transition is very similar to the Pomeranchuk effect in helium-3. So here we have fermions. Helium-3 is a fermion because it has a nuclear spin. And we have a phase where we can go from the solid into the liquid upon cooling. So we can melt a solid into a liquid, which is uncommon in our daily life. And in a Mott insulator, it's the same. We have a solid of electrons, and here we have a liquid of electrons. Mott insulator not moving, metal electrons are moving. And in the physics is from the Hubbard model. So we have tight binding term from the bandwidth, and we have the Coulomb repulsion, which prevents to have double occupancies. So if we create a double occupancy, we have to pay potential energy U. But if the delocalization is big enough, then we don't care about this anymore, and then the electrons can move. And the transition is simply done by changing the distances, and therefore we have more wave function overlap or less wave function overlap, and we can go from the insulator. Importantly, yes, this we have seen already. We can compare the phase diagrams of different materials. For instance, this compound in black, we can measure the width of its electronic transitions, which is a measure of the electronic bandwidth. So by optical spectroscopy. And we can do the same for the compound in blue. And we see that the compound in black has a much smaller bandwidth than the compound in blue. And therefore, we have to rescale the temperature and the pressure scales. And if we take into account the electronic bandwidth properly, we see that the compound in black and the compound in blue can be merged into a common phase boundary. So they really sit in the same phase diagram, just in different places, and they cover a different range. And if one can determine the bandwidth and the Coulomb repulsion from optical spectroscopy, this is accessible, and this is how we eventually made this phase diagram. Good. Let me quickly show the charge ordering in quarter field systems. So if we have what we saw so far is half filling. So if we have one lattice site being a dimer of two molecules, like two molecules here can host one electron, and therefore this is a half-filled band. So on this lattice site there could be at most two electrons, so it's half-filled. If we have individual molecules, due to the chemistry, each molecule must have plus 0.5 charge, and this means that you have half a charge per one side or one charge per two sides, but you could have for two sides up to 4 charges, so you have only 1/4 filling. And as a result, in a half-filled system, you build a Mott insulator, so double occupancies are the relevant potential energy. In a quarter-filled system, you build, or when you move a charge, you don't create double occupancies, but you pay this off-site, so inter-site Coulomb repulsion B. And this is favoring a situation where the charges are far from each other. So you have here a lot of charge, here you have no charge, here you have a lot of charge, etc. Well, you can have it also on a 1/3 filled lattice, which would give something like a honeycomb in a triangular lattice, but these are details. And for the quarter filling, there are a lot of these organics which realize quarter filled lattice, like the theta or the beta double prime. So with plus and minus charges. And the organic molecules, if you have a lot of charge on a molecule, it will feel a different resonance frequency, because the resonance frequency between one carbon and the other, you can measure this vibration mode, and this way you can probe how much charge is sitting on each molecule. And therefore, if you have a material with the same charge on each molecule, you will have one vibration mode. If you have different charges, then you have one peak for the plus charge and one peak for the minus charge. So you can quantify how much charge you have on each lattice site. And if you do it properly, you can measure the spacing between the different peaks. So one molecule has an ionicity of half an electron, another one of a third electron, another one of even less. And here you have, therefore, a lot of ionicity, and here you have almost no ionicity, and you end up in a metal. And if the critical value of ionicity is reached, you have this metal-insulator transition. Yes. And one question which was of interest was, is the superconductivity here coexisting with the charge order or not? for this, we made a very comprehensive measurement. So we had to measure the resistance of the sample during our optical measurement. Here we see the measurements at different points and in time. And for instance, during this data point, we measured these vibration modes. Here we have one peak, here the other, with the essence that we always have the splitting. So the charge order is always there, and the sample, even though the sample becomes superconducting, even though we are here in the superconducting state. Good. And yeah, then the last thing, at low temperatures, Mott insulator, now we are back at half filling, has an antiferromagnetic state because exchange interaction depend on P squared divided by U. And this is the origin of magnetism in vanadium oxides and cuprates and also in the organics. Now we can ask the question, what happens if we put the spins not on a square lattice where they can form this antiferromagnetism, but on a triangular lattice. And interestingly, if you have no magnetic order, this insulator has more entropy than the metal. So this is the Pomeranchuk effect, which we saw before. And we can destroy this magnetic order. And this is something which is quite interesting from a physical point of view. So, because on a triangle, you can never have all these bonds antiferromagnetically aligned. So magnetic order does not form. And it was suggested that you can have a resonating valence bond state with itinerant spin excitations, possibly used for quantum computers, although it is quite far-fetched. Yeah, and there are some organics which look like this. So organic conductors like this one have a triangular lattice of these molecular dimers, and this looks exactly like a triangle. And indeed, this material, it does not show any change of the magnetic properties, whereas a square lattice material shows a splitting of the NMR peaks. It is antiferromagnetic. So yeah, indeed, the triangular lattice material does not show antiferromagnetism. So this one can really suppress it, but the question is whether it is a spin liquid. In this particular case, we showed that it is likely not the case. Yeah, and then we applied some strain tuning, but let me come to the end now. Yes, organic quantum materials are highly tunable. We can substitute the molecules, we can apply pressure. We can use pretty low pressure for this. So from 100 bars up to a few kilobars is enough already. We can apply strain and we can even dope them. And this way it allows us to study all these correlated electron phenomena. And both in 1 dimension, 2 dimension, and yeah, this way I'd like to thank you for your attention. And please, if you have questions.
Thank you. Any questions?
So I noticed in your diagrams, I'm not sure, I'm not really sure, but I noticed that probably this superconductivity region arises at in the situation where you already have effectively three-dimensional system, right?
So the quasi 2D systems that we look at, let me. You are referring to these quasi 1D systems, right?
Yes, quasi 1D to quasi 2D, then eventually become three-dimensional systems.
Yes, yes. I think it was somewhere here. Yeah. In the case of these compounds, this is right. But let me say, in all cases, I mean, these systems would not exist as a two-dimensional layer. And there is some finite interaction between the neighboring layers or the neighboring stacks. So, essentially the energy scale of this third layer is, or the interaction between one layer and the neighboring layer is typically higher than temperature in the range where it becomes superconducting.
But, okay, so when you say interaction, what does it mean? Is it Coulomb interaction or some other type of interaction, or it's conduction?
Transfer integrals.
Okay, just
yeah, there are transfer integrals which are along the layer, along the stack, so transfer integral hopping from here to here. But if you have next to this stack, you have another stack, then there's some small transfer integral going here. It's not 0, but it's of order 10, 15 Kelvin, and this is certainly higher than the superconducting.
Okay, thank you.
Any questions? Maybe also have one about experiments with pressure when you glue your material and then you apply pressure. So the question is that you change the range of temperature, the range is quite big. What happens with the glue and what is glue exactly, which can exist and function?
Yes, so first, if we apply pressure with helium gas or oil pressure, we do not glue anything. There's just a pressure medium, like a liquid as we showed here, and yeah, they are just in this medium. But you are referring to the uniaxial strain experiments?
Yeah, I guess it was one plot when where I changed the temperature from 200 K to 500 K.
This was with oil pressure cells. This was on vanadium oxide. Yeah, this was this year, and this was done with oil or even gas. No, it must be oil pressure cells. Yeah.
Okay. So you don't vary temperature so much when you use glue.
With these organics, we typically, since the physics is at, I mean, 300 Kelvin is covering the entire phase diagram, so there is no reason to go to higher temperatures. And also, you should not go, because organic materials, if you heat them up, they are not that stable. So they would just fall apart at 100 Celsius, let's say, 400.
Okay. And maybe one more question.
But regarding the glue, this glue for the strain measurements, so the stuff on the right and on the left, this is die-cast. This is a glue which people use in construction, like on the street, and it's a very hard material. It is also to some extent organic, I think, or some epoxy type material. But yeah, since we are cooling down only, this is typically fine.
Okay, and one more question about the choice of material. So at some point you show the periodic table and you show that you used 3 materials which are in your column. And then the next one, it was from the different column. Yeah, I just wanted to ask why didn't you continue?
I guess in this particular case with I mean, the question is always: is the chemistry allowing to make this type of anion? So I think PF6, ASF6, and SPF6 are very standard anions that you can easily get. I'm not sure about bismuth F6, whether this is so stable. But in the end, you can just check how the ionic radius is for this entire molecule. And I think from tantalum F6, the ionic radius is a little bit bigger than for antimony F6. So it does fulfill more or less. I mean, actually, if you compare, here we are in the, so we have a filled S and D bands, and then we have 1, 2, 3 electrons in the P band. And here we have 1, 2, 3 electrons in the D band. So in principle, from the chemistry, tantalum should be similar to antimony.
First of all, thank you for the talk. I just have a technical question for the pressure measurement you did. I guess you use a duct cell for applying pressure to the sample, diamond anvil cell?
Actually, no. I mean, people nowadays do this, yes. But diamond anvil cells, they typically reach pressures of order several GPa. So like several GPa. I mean, 1 GPa is 10 kilobar. And these organic compounds, you can get this phase transition here already at about 1 kilobar or even less. So if you have a pressure cell which is focusing on high pressures, you don't have a very good resolution in the pressure. And therefore, it is useful to use these oil pressure cells, which cover a smaller pressure. And even also these, helium gas is even more precise in the pressure resolution, because we want to have a lot of data points right around this range. And if we have this diamond anvil cell, we would probably have 1 point here and 1 point here. And because the materials are very soft, we need small pressures, and therefore diamond anvil cells are not the primary choice.
And there were steady-state measurements, or in situ measurements.
Of the pressure itself?
The pressure.
Yes, typically this is done, yeah. So I think with, I don't recall the particular wire what is used, but I mean some resistive material. Or if we do optical measurements, then, for optical measurements under pressure, one uses a diamond as a window and gets the infrared through and back. And then for the pressure gauging, one uses some ruby, so the resonance frequency of a ruby, and otherwise some material which changes resistance upon pressure.
Because ruby does change at pretty high pressure, so I am aware that, for example, samarium crystals are more sensitive for the lower region of the pressure.
I believe different groups are using different things. One setup I know they used ruby, but yes, certainly others can be applied. And at very low temperatures, one could use something like the superconductivity of tin, for instance, because this is also pressure sensitive, and but many choices.
Thank you.
I also discussed this phase diagram with the quasi 1D, quasi 2D.
Mm-hmm.
So, but what's the phase? It's described by LOC, this loc.
Localization. So where was it? Here. In these quasi one-dimensional systems, at high temperatures, it is a metal. So let me draw. So if you look at the electrical resistivity, function of temperature, it first increases with temperature, then it shows a minimum and it goes up, and this is T log. And essentially this dimer here, so two molecules can host one electron, and there is some dimerization, so the distance between these two molecules is different than the distance here. Mm-hmm. And therefore, one electron is then sitting here and another one sitting here, and it's like a Mott insulator. So it has more the properties of a half-filled system than of a quarter-filled system. So you have one electron here and one electron here, and you don't want the electrons to hop from here to there. And this is this transition. But at lower temperatures, there's another transition that you want to have a lot of electrons here, not a small charge here, a lot charge here, and a small charge here. So that you have this charge ordering which I described in the This is the CO. And for the charge ordering, the resistance shoots up much more than for this Mott localization. Yes. So it's a mixture of everything.
Yeah, I mean, like, I was just wondering because, like, for this 1D system, I believe, because you said fluctuations are important, so, like, the order might be suppressed. So, like, and it seems it just, like, doesn't go to the ordered phase, first goes to just, like, 2D, quasi 2D system. And
I mean, in one dimension, the point is you cannot have a proper Fermi-liquid, a proper metallic state. So instead, you need to describe it with a Luttinger liquid. And this means that you don't have quasi-particles, but you have exponential power law dependence of conductivity and all these other properties. So you don't have this T-square dependence of resistivity, for instance. Yeah, this is in the 1D range. You can study this 1D physics, and people did even see spin charge separation as predicted. So these materials, all this was done, but more than 20 years ago.
And I just like one small question. When you said the D wave superconductivity, what exactly you meant? That there is a gapless superconductivity?
Let me go somewhere where we have this. No, we had it before, I think. Yes. So if you have a d orbital, I mean, you have this negative and positive sign of the wave function. We call it d-wave superconductivity because, I mean, this would be x squared minus y squared symmetry. So the along the x and the y direction, we have large amplitude, and along the diagonal, not much. And the point is now that this is indicating the size of the superconducting gap. So the superconducting gap forms, so if you have a Fermi surface here, then you form a gap between, I mean, a gap, so you don't have Fermi surface anymore. And the size is largest along the x or the y direction. But if you go from the x towards the y direction, when you go from minus to plus, you must cross 0 at some point, because the phase is different, and this means that your superconducting gap must have a 0 node. So if we have the gap as a function of momentum, or we could just call it angle phi in this case, then here at 45 degree, 0 degree, and here 90 degree. So the gap is large at 0 degree, then it goes to 0, and then it becomes large at 90 degree again. And because we have here no gap, so this means that here we have common electrons, which are so metallic electrons. If we apply a magnetic field or temperature, we have some energy scale here. Energy can be kBT, or it can be Bohr magneton times magnetic field. And we more or less linearly excite quasi-particles. The higher energy scale we apply, so the higher temperature we have, or the higher magnetic field, we have more quasi-particles which are not superconducting. And these quasi-particles then give rise to some relaxation. And yeah, in the end, when we take into account the proper laws from NMR measurements, we find that this linear temperature dependence of the number of states that contribute, because we have these gap nodes. And this is the same in cuprates.
Right, but like you are not restricted by the D wave only. Or I mean, like the D wave superconductivity.
Well, nodal superconductivity, let's say, yes. I mean, whether it is in the organics exactly x squared minus y squared, or xy, or maybe some other nodal superconducting state, this is not known. Measurements on the superconducting order parameter symmetry are pretty difficult, also for the inorganic systems, and for organics the samples are more challenging, so the experiments are usually not that easy or not possible. But if we just take into account specific heat and NMR and all these standard measurements, it looks the same like in the cuprates.
Okay, thank you.
Yeah, and so this is the case of quasi two-dimensional systems. In the quasi 1D systems, I'm not sure. But the quasi 2D systems are studied best, let's say.
I would propose to move further discussions to apero, and let's go to again.
Yeah.